All right, welcome students to another review. This will be uh, the review part of what we learn in chapter 5. Okay, so in chapter 5, we're talking about linear inequalities and systems of linear inequalities and eventually linear programming. Okay, so to get started, um, to graph a linear inequality, we need a couple of things. We need a boundary line. So we need a boundary line. We're also going to need a test point. And we are going to have a solution region. Okay. So let's see, maybe I could go ahead and give a small lecture as I complete this particular example. So in this example, we're trying to graph the inequality y is greater than or equal to x plus 1. In this particular case, the first thing I'm going to do is talk about the boundary line for this inequality. The boundary line for this inequality will be the line y equals x plus 1. So basically what I did here is I replaced the inequality symbol with the equal sign. This boundary line is going to be solid because the inequality symbol has the equal to. And I'll try to explain what that means in the actual graph. So to graph this line, we're looking at the equation of a line in the form y equals mx plus b, where m represents the slope or the steepness of the line, and in this case, b is the y-intercept. So for this particular line, the coefficient of x is equal to 1, so the slope is equal to 1. In fraction form, that will be 1 over 1. The y-intercept, b, is equal to 1. So with these two pieces of information, that should be enough to graph the boundary line. The y-intercept is 0, 1. So I plot this point. With the slope, we can then navigate in the graph to get a couple of more points. So in this case, the fact that it's positive, we can go up and to the right. So up 1, to the right 1, up 1, to the right 1, up 1, to the right 1. Or we could have said down 1 to the left, that is the same movement. I'm going to connect these points with a solid boundary line. Okay, so okay, there it is, and I'm going to extend this line here. So what this boundary line has done is taken our graphing grid and broken it into two halves. Call this the upper half plane. And then down here, we can call this the lower half plane. One of these two areas will represent the solution to this inequality. So we just graph the boundary line. Now we need a test point. In this particular case, we would like to choose the easiest point to test on our inequality. I suggest that we select the point. I'm trying to pick another color here, but for some reason this is kind of in the way. So I'm not sure how that's going to work out. So I'm trying to pick another. All right, here we go. So let's choose another color here. And the point that I want to choose will be 0, 0. we choose a test point that is not on the boundary line. So I'm going to call this point 0, 0 my test point, and I'm going to plug it into the inequality. So this will be the x value. This is the y value. So 0, is it greater than or equal to 0 plus 1? And it turns out that this mathematical statement is false. Therefore, what's the conclusion? It means that just by testing this one point in the lower half plane turns out to be false. Therefore, every point under the boundary line will be false. Now, I leave it up to you if you want to test a few more points, but one point is enough. So what does that mean on the other side? Well, that means that on this upper half plane, every point will make the inequality true. Now, I don't want to test too many points, but I'm just going to test another point on this upper half plane just to show you that it is going to satisfy the inequality. So for example, let's pick the point, in this case, 0, 4. And we'll plug it into the inequality to show us, or to prove to ourselves that it will be true, that it will make the inequality true. So in this case, the y value is 4. Is it greater than or equal to 0 plus 1? And 4, in fact, is greater than or equal to 1. This is true. So therefore, this entire region up here, this entire upper half plane, will be shaded. Now, I don't really do a good job of highlighting, but let's see. Maybe with this technology, it can be done a little bit easier. Let's see. I want to just do that. So, I don't know about that. So, of course, something that looks like this. So all of this area up here, all of these upper half plane will be part of the solution. Any point in this region will satisfy the inequality. So what about points on the actual line? Well, the fact that this boundary line is solid, every point on the boundary line will satisfy the inequality. Okay. All right, let's move on to another example. Okay, so hopefully that message will go away there. It says, determine whether the point is in the feasible set, in other words, in the solution set of this system of inequalities. All right, so how can we get rid of this so I can, nope, I don't want to do that. Okay, wow. All right, so the idea is that we're going to have to take this point, this will be our test point, and we're going to have to plug it into each one of these inequalities here. And if it is a solution to this system, then it will satisfy all of the inequalities. Don't forget that this is your x and that is your y value. So plugging it into the first inequality, we have 6 times 6 is the x value plus 2 times 7. Is that less than or equal to 75? 6 times 6 is 36 plus 14. Is that less than or equal to 75? 4 and 6 makes 10. Carry a 1, 3 and 4, that will make 50. And 50 is in fact less than 75. So this is true. Plugging it into the second inequality, we have 6 plus 7. Is it less than or equal to 15? 6 plus 7 is equal to 13. And again, this is also true. Third inequality, 2 times 6 plus 6 times 7. Is it less than or equal to 59? Here we have 12 plus 42. Is it less than 59? And here we have, close, 54 is less than 59. Only the x value, so the x value was 6. Is it greater than or equal to 0? That is true. Only the y value is 7 greater than or equal to 0, and that is also true. Since the point 6, 7 satisfied all of the inequalities, therefore it is in the solution set, or what is referred to as the feasible set. Example 3. Graph the solution of the following system. So what we're going to do here is we're going to graph these two inequalities on the same grid, okay? So the first inequality is 4x plus y is it greater than or equal to 8? And so therefore, the first thing we're going to do is talk about the boundary line. The boundary line will be the line 4x plus y equal to 8. In this case, to graph the line, I'm going to use the x and y intercept. So how to find the x and y intercept of this line? To find the x-intercept, completely forget about the y and solve the equation of 4x is equal to 8. After dividing by 4, we get that the x-intercept is equal to 2. In order to graph a line, we just need 2 points, so I tend to find the x and y intercepts. To find the y-intercept, completely forget about the x term and write the equation y equals 8. There's nothing to solve here. The y-intercept must be the positive a value. Now, once again, the boundary line will be solid for this example because the inequality symbol includes the equal to. If you're wondering, so what if it doesn't have the equal to? What if it's just greater than or the less than? In that case, the boundary line will be dotted or dash, okay? But that's not the situation here, since the inequality symbol has the equal to part of it, the boundary line must be solid, okay? So I'm going to connect these 2 points with a solid boundary line. Okay, so I'm doing my best here. And every linear inequality needs to have some shading, a solution set, an area that is colored or highlighted. In order to do that, I always choose a test point that is not on the boundary line. So hopefully you and I can agree that 0, 0 seems to be like the easiest test point here. Plug it into the inequality. 4 times 0 plus 0 is it greater than or equal to 8? Everything on the left turns out to be equal to 0. And 0 is not greater than 8. This is false. Therefore, the entire lower half plane will be false. Therefore, we are highlighting everything on this side. Okay. All right, so I'm going to try to do this to the best of my ability here, and hopefully I won't make a mess out of this. Don't forget that this is only halfway through the example because we need to graph another linear inequality. So this is just halfway through. This is half the work because now we need to graph another linear inequality, which in this case is the linear inequality x is less than or equal to 2. The boundary line, once again, is solid. What is the boundary line? The boundary line is x equals 2. This is the equation of a vertical line that passes to the x value 2. So it's a solid boundary line that passes through 2. There we go. And now we either color to the left or color to the right of this boundary line. If we were to choose what we're looking for, I think the inequality here tells us which way to go. We want to choose points that are less than or equal to 2. Those must be the values to the left of the boundary line. So therefore, we have something that looks like this. So in this case, this is considered the left half plane. So we are shading, coloring everything on the left half plane. But as I do this, did you notice that there was an area where both solution sets intersected? And if you did, kudos to you, because that is the area that that is the solution set for this particular example. The solution set for this system of linear inequalities is the intersection of the solution sets. So in this case, right, even though it's kind of difficult for me, but this is the only part of the graph that you will actually keep. Everything else must be deleted. So we only keep the part where the two solution sets intersected. Okay, let's go ahead and keep going here. We have another system of linear inequalities. So we are going to do some coloring, but eventually we're going to have to trim if there is an intersection of solution sets. The first boundary line, the first inequality is x minus 3y is greater than or equal to -3. The boundary line will be solid, and the equation will be x minus 3y is equal to -3. The x-intercept will be x equals -3. The y-intercept, notice how we just completely get rid of the term and we keep -3y is equal to -3. After dividing by -3, we get that y is equal to 1. So there it is. We need to choose a test point. Again, a point that is not on the line, and hopefully you and I can agree that 0, 0 is a good test point because it is not on the boundary line. Plugging the test point into the inequality, we get 0 minus 3 times 0 is it greater than -3. The left side turns out to be 0, and 0 is greater than -3. So we are going to highlight in this case, will be the lower half plane. Okay, so we have another linear inequality that we're going to graph on the same grid. And let's see what that's going to look like. So let's choose a different color here. Let's choose this color. And we have the linear inequality 2x plus y is less than or equal to 4. The boundary line, once again, it seems like I'm only picking examples that have solid boundary lines. And that boundary line will be the line 2x plus y is equal to 4. The x-intercept, 2x is equal to 4. Again, completely get rid of the y term. Divide by 2, x is equal to 2. The y-intercept is just y equals 4. Again, it is a solid boundary line, so we're connecting these 2 points with a solid boundary line. And now we need a test point. Hopefully we can once again agree that 0, 0 will be a good test point because it is not on the boundary line. And plugging it into the inequality, we have 2 times 0 plus 0 is less than or equal to 4. The left side is just 0, and 0 is less than 4. Therefore, we will go ahead and highlight this entire region. But as I'm doing this, are you noticing that there is an intersection of the two solution sets? Well, in this case, I'm going to continue my coloring, and then I'm going to only keep or trim, edit, crop the area where the two solution sets intersect. So I'm going to use a different color for that, but let me finish coloring this. This is my best second grade coloring skills here. Now I'm going to choose a different highlighter to highlight only the area where the two solution sets intersected, which is this. All right, so let's see my best second grade coloring going on right now. Okay. And so therefore, that's the only thing that I need to keep on my graph. Everything else needs to be gone. I'm only keeping where the two solution sets intersected. So therefore, trim, 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 trim. And notice that we're only keeping the area where the two solution sets intersected. All right, well, let's go ahead and continue with some other examples. Number 5. Number 5. It says to solve the system graphically and indicate whether the solution set is bounded or unbounded. Find the coordinates of each corner point. So here we have an inequality, another inequality, and another linear inequality. Let's begin with the first linear inequality. We have 2x plus 3y is less than or equal to 12. The boundary line will be solid. What is the boundary line? 2x plus 3y is equal to 12. This line has an x-intercept of 2x is equal to 12, dividing by 2, x is equal to 6. The y-intercept of this line is 3y is equal to 12, dividing by 3, y is equal to 4. So we have 6 as the x-intercept and 4. So I am going to connect these 2 points with a solid boundary line. Okay, so we got something that looks like that. And I am going to hold on the shading until I finish graphing these 2 other linear boundary lines. Let's just call it for now, just stick to the boundary lines. And that's actually the x equals 0. That would be the y-axis. So this turns out to be x equals 0. And this turns out to be the boundary line y equals 0. So that is the x and y axis. And it turns out that if you select, in this case, the a test point, okay, you cannot use 0, 0 because 0, 0 is on these boundary lines. So maybe you choose something simple like 1, 1. Will 1, 1 satisfy all 3 inequalities? Well, let's see. Let's see if we can test this real quick. 1 will be greater than 0, and 1 will be greater than 0 because this will be the x value, that will be the y value. Okay, so that's so far so good. Let's see if it holds on this inequality though. 2 times 1 plus 3 times 1, is it less than 12? 2 plus 3, that's equal to 5. And 5 is less than 12. So therefore, this will be our feasible region, our solution set. And notice that it is enclosed, okay? It is enclosed, it is somewhat bounded by this triangle shape that is made by the 3 boundary lines. So this is a bounded example, okay? So what we want to put here is we're going to put it is bounded, okay? And the corner points, I think what you want to do here is you want to just write out 0, 0, comma, 0, comma, 4, comma, 6, comma, 0. So those will be the 3 corner points. All right, it says type an ordered pair, use a comma to separate answers as needed. So just like I did here. All right, and so therefore that example kind of leads into a linear programming example where we need to graph something very similar to what we did in example 5. And let's see how to take care of something like that, okay? In a linear programming example, okay, we want to either maximize or minimize an objective function. In this case, this seems to be the objective function. And we would like to maximize that objective function. So therefore, we need to, this objective function is subject to this particular constraints. So our job will be to graph this system of inequalities, and then we need to find some corner points. But let's just focus on actually graphing this system of inequalities. So let's see. We have seems like all of the lines will be solid boundary lines. So let's see, we have 2 plus y is equal to 12. And trying to work this out quickly, the x-intercept will be 2x is equal to 12. After dividing by 2, x is equal to 6. The y-intercept in this case will be y equals 12. I'm going to move on to the next inequality. It seems like, oh, that was easy. X plus y is equal to 7. So I'm trying to figure out what these boundary lines will look like. And so therefore, x is equal to 7, y is equal to 7. And we got one more boundary line here, which is x plus 2y is equal to 10. The x-intercept is x equals 10, while the y-intercept will be equal to 5. This last inequality just tells us that we are going to be in quadrant 1. So I'm going to give myself a picture of quadrant 1 only. And here we go. Maybe we can use some colors. So let's see. We have 6. I'm going to say that this is 6. Oh, so my graph is going to be, and let's say that this is 12. And so there is one boundary line. And then I'm going to use a different color now where I need 7 and 7. So I'm going to say that that's 7. I'm going to say that that's 7 somewhere there. Oops. Oh, notice that they intersected at some area there. Okay, so I'm going to have to find that point of intersection. And then we have 10, 5. So let me see if I can. So we have then 10, and then somewhere here, 5. What a very very poor sketch here. Wow, what a poor sketch. Okay, it would have been nice if I would have used maybe some graphing paper. That would have been better. But it is what it is for now. And so therefore we got something that looks like that. So it seems like there's a whole bunch of corner points here. And so, let's see. Let's see. Not necessarily that I wanted this to be 30-minute example, but let's see if we can find these points of intersections rather quickly. 2x plus y is equal to 12. And here we have x plus y is equal to 7. So I'm going to try to solve this system real quick so that way I will know when these two lines intersect, which is this point right here. And so let me go ahead and multiply by just -1. And we get 2x is equal to, in this case, of 5. Oh no, 1x. I'm sorry, that would be 1x. So x is equal to 5, and therefore y has to be equal to 2. Okay, so this point of intersection is 5, 2. Let me see, let's go ahead and find another point of intersection here. Let's do 2x plus y is equal to 12. And I'm going to set it equal to x plus 2y is equal to 10. In this particular case, what I'm going to do is I'm going to take the bottom equation and multiply it by -2 so I can get rid of the x values. So 2x minus 4y, this is minus 20 here. I want to be careful. And then we get x's go away. And then we have -3y. And then 12 minus 20, that's -8. Y is equal to 8/3. Oh, what a nasty point right there. And so therefore, and therefore now we need to find, oh, what a poor example. And then so let's go ahead and now find x. So x plus 2y is equal to 10. X plus 2 times 8/3 is equal to 10. Oh, wow. Not only that, but it seems like I'm running out of room to show all my work. X plus 16/3 is equal to 10. And therefore, x is equal to 10 minus 16/3. Getting a common denominator here of 3, we get 30 minus 16, which is equal to 14/3. Wow, so therefore this point right here happens to be 14/3, comma 8/3. All right. So that would be, I'm just checking something here. The feasible region, let me delete this real quick, okay? All right. Again, my sketch is so poorly, I should have done it on much. But keep in mind that in this particular example, let me see if I can use it, this color right here. If you test 0, 0, okay, it will be this region right here. It will be this region right here. Okay. So this will be the space where all of the solution sets will intersect. So in a linear programming example, only one of the corner points will maximize or minimize the objective function. Okay. So in this particular case, this region that we created, okay, has 4 corner points. Has 4 corner points. And those corner points will be 0, 0, which I am pretty sure that will not maximize the objective function P. We also have 0, 5. We also have 6, comma 0. And we also have now what we know to be 14 over 3, comma 8 over 3.